So here we are, we're still in section 4.5, but now we're going to take a look at definite integrals. So there's two ways to do this. Our answer will still be a number, or it will be a number because it's a definite integral. But we see that in this case we've got that inside raised to the third power. We don't want to multiply that all out and then multiply it through by x and take the antiderivative of each piece. Like, that would be a lot. So instead we'll use the substitution method. We'll make the inside our u. Our du will be 6x dx, and so that means that x dx, which is what we need to replace with u or du, will be 1/6 du. Now here is the first way. So I need that for both the ways that I'm going to do this. But the first thing I want you to see is when I rewrite this, I'm going to rewrite it as 1/6, looks like u cubed du. However, I'm not going to put limits of integration on it right now because they are not the same limits of integration. U and x are two different variables. So u doesn't go from 0 to 1. X goes from 0 to 1. So I'm going to leave it like this right now. And then I'm going to take my antiderivative. So we're going to get 1/6 times, and then the antiderivative of u cubed would be 1/4 u to the 4th. And I mean, you can put a plus c on it, but with the definite integrals, you'd have a plus c and then you'd have a minus c. The c's are going to be gone with the definite integral. So technically this is true, but it's 1/24 u to the 4th plus c. But what we're trying to do is, this is the same as 1/24, and then we'll replace our u, 3x squared plus 1 to the 4th plus c. But what we're trying to do here is we're trying to take 1/24, 3x squared plus 1 to the 4th, and we want to evaluate that from 0 to 1. I mean, that's the whole point of this. So now that we have our antiderivative in terms of x, now I can evaluate that from 0 to 1. So I'm going to write 1/24, and then I plug in 1, and you can see we'll have 4, so it's 3 times 1 plus 1 is 4, 4 to the 4th, minus what happens when we put in 0, so that's just a 1 to the 4th. And then we can evaluate that, multiply that out, evaluate it, and we're going to have 85/8. Okay, so that's one way to do it. The second way is, once you have your 1/6 u to the cubed du, you can think about putting limits of integration on it. So the idea is, if x equals 0, that's my lower limit of integration, then that means that u equals 3 times 0 squared plus 1, or u equals 1. So that tells me that if I'm talking about u, my lower limit is 1. Then, when I put in x equals 1, because that's the upper limit, that means that u would be, as you can see, 3 times 1 squared plus 1, just based on what u is equal to, and that's going to be 4. So the point here is, if x goes from 0 to 1, that's the same as u going from 1 to 4. And now I don't need to even take this problem back in terms of x. I can just use it as it is. So that's going to give me 1/6, and then I have u to the 4th divided by 4, or times 1/4, from 1 to 4. And what I really want you to see is that this is exactly the same from what we've kind of already been dealing with here, if you think about it, because when we do 1/6 and we put in 4, that's going to give me 4 to the 4th over 4, or 4 cubed, and then I have minus what happens when we put in 1, which is just going to be 1/4. And what you'll find out is that if you do in fact do this, you're going to get 85/8. So the answer is the same. And the idea there is, again, these two things are equivalent. It's just one of them you're kind of doing a little more of the work right in the beginning, and in the top one you're doing a little more of the work at the end. But they get you to the same place. So there you go. Okay, so taking a look at this example, the next example, let me give a little space here. So notice you're going to need to use something else besides our rules. You have two trig functions that are being multiplied together. You don't have an antiderivative for them, that's obvious. And if you think about it, even if you were to try to rewrite it, everything's being multiplied together. You don't have any fractions here that can be rewritten. You could arguably rewrite sine squared x as 1 minus something, but then you're still going to have a sine squared and a cosine squared. So the way to think about this is, that the derivative of sine is cosine and the derivative of cosine is negative sine. So there's probably some aspect of a relationship there where you can think of u and du. Now, because sine is cubed, that's really telling us I should make u be sine x. Because again, you can't have du cubed. These values, the du, the dx, are always sitting at the end of the integral. They can't be in numerators, they can be in numerators, but they can't be in denominators or inside something or raised to some exponent. And so if u is sine x, then du is cosine x dx. So notice that allows us to change this whole piece here to du. And then we can take part of this here, the sine x, and have it be u, and now just have u cubed. So I'll do the second method again to show you that we can change our limits of integration. So we have u cubed du, but I'm not going to go 0 to pi over 2 because that's not what u goes, those are not the limits for u, those are limits for x. So if x equals 0, then when I put 0 in for x, that tells me that u equals 0. That's not bad, okay? And then if x is pi over 2, that tells me sine of pi over 2 is 1. So my limits have changed from 0 to 1. And now I can just take the antiderivative without going back to x. So I have u to the 4th over 4. I guess you just saw that, 0 to 1. And that's going to give us 1/4 minus 0. So we end up with an answer that is just 1/4. And of course, you could take it back and then, take it back to x if you wanted to, and then put on your original limits of integration, 0 to pi over 2. You're going to get the same thing. Now, I want to show you that the next example is exactly the same. The only difference, take a look, only difference right here. So notice there's a picture here and it says we're adding up this area and this area. And if you were with us for the last section and talking about total distance and total displacement, you might notice that in this case, it really looks like you have two pieces that are the exact same size but are on either side of the x-axis. So that may be thinking, when I evaluate this, since I don't have any kind of absolute value, what's going to happen? So remember, we already have the inside of this, it's u cubed du, so I'm just going to use the same because it's the same problem from above. So I have u cubed du. In this case, if I think about changing the limits of integration, so x equals 0, u is still 0. Again, I'm just using the substitution I made before. In this case, when x equals pi, u equals 0 again because u is sine x and sine of pi is 0. So you're actually integrating this. And we've talked a little bit about this already, but if you're going to integrate over the same interval, like 0 to 0, which has, no width on it, your answer is going to be 0. And so that's what you get. Even if you were to put it back, it's what you're going to get. It's just what it is. So a couple useful properties. If f is an odd function, so notice we're going from if f is an odd function. So the first thing that has to happen is this has to be an odd function. So you have to be able to show that that is odd. Once you're able to show that is odd, if you're going from some value that is negative to some value that is positive, so you're on either side of the y-axis, you want to remember that odd functions are symmetrical over the origin. So what that means is you're going to have the same amount of area here that, or because you guys are mirrored to me, here that you have here. And because of that, this answer will be 0, always. You just have to show that you have an odd function. Now, if f is an even function, the same is not true, because an even function is going to be symmetrical over the y-axis. And so the only thing you can really tell, which might be helpful to you, is that you'd have double the amount of area if you just take one integral from 0 to a. And that might be a little bit easier, so why not do that? It could be. And so that's another useful property that we have, depending on even and odd functions. All right, so we'll take a look at a few examples here. And if you're ever given a function, I had a student that, no joke, before I even taught Math 5A, like he came to my Math 5A on the first day. He had already been in Canvas. He had already been working through the final review because he basically taught himself calculus, before he even showed up on the first day. And because of that, he's like looking through the final review, and this was one of the problems, something similar to this. And he said, I don't know how to do this problem. And I said, well, there's reasons for that. You're not actually expected to like do it. And that's because the things that should kind of trigger you are, oh, I have -3 to 3. So we're going from one side of the y-axis to the other side, same amount of distance. And then the point would just be to show that you have an odd function. So it wouldn't be enough just to like bust out a 0 and be like, it's 0. But if you put in a -x, you're going to have -x cubed. You're going to have plus -x. You're going to have cosine -x. In this case, that's going to give you a -x cubed minus x. But cosine is an even function. So you get cosine x. So cosine -x is just cosine x because of the symmetry on cosine. And we can pull out that negative from the numerator to get x cubed plus x divided by cosine x. And we see that our original function and our function with -x are just differing by a negative. So that's what tells us that that function is odd. And then we can say that the area there is 0. For the one below that, we have -1 to 1. It is a pretty basic even function. So the idea here is you could, if you wanted to, rewrite it as 2 times the integral from 0 to 1. And just picture this, it's a parabola on each side. So the area underneath where it cuts off at 1 and the area where it cuts off at -1 are going to be an equal amount of area there. So we just write it like this instead. And again, this, you might find that this is just an easier, slightly easier integral to do if you have an even function. So we're going to have 2 where we will have, x cubed over 3. We're going from 0 to 1. This is multiplication here. It is a definite integral, so I'm not going to worry about plus c. We have 2 times, and then we have 1/3 minus 0, and that's going to give us 2/3. So it's just that each side is a third, and so we just multiply it by 2 and we get 2/3. All right, almost done. Okay, so find the area. So sometimes you'll see problems that say something about finding area, and that should just trigger, hey, I got to do an integral here. And you're given the limits of integration, 0 to 4. You're given what should be inside the integral, because this is the function here, plus 9 dx. So your job is to set it up like this. So if you want, totally welcome to pause this and take a minute, a couple minutes, and see if you can use the substitution method on this to get an answer, changing to u if you want, and or not, and seeing what number you get. So one thing to notice is we have this thing inside the square root. Key thing, if I didn't have this x right here, if that was not there, then I would have no way to do this. It is not like a half circle or anything like that. And so this x is required in order for us at this point in time to do this integration at all. So kind of a key thing to see. Now, not surprisingly, u will be the inside of that root, because when we find du, that's going to be 2x dx. And by dividing by 2, I get 1/2 du equals x dx. So I'm going to be able to replace my x and my dx. Notice that every time I've done these problems, I've always included, if there was something inside a trig function or in a denominator or raised to a power, the constant always gets included, because the derivative, when you take find the differential there, that constant's always going to be gone. And so it's always good because it will simplify your original function that you have inside. So it looks like we're just going to have the square root of u, which is very exciting. Du plus a little 1/2 here on the outside. So we have, and actually I should not have that equal because I don't have the limits of integration on it. But I guess I could put the limits of integration on it. Why don't I just do that? And then it'll be equal. So if I let x be 0, u is going to be 9. If I let x equal 4, u is going to be 25. So I'm going to have 9 to 25. This is all just based literally on this piece of information right here. So now I have 1/2, and I have, this of course is u to the 1/2. So that's going to be 2/3 u to the 3/2. That I'm evaluating from 9 to 25. So I have, well, that's going to simplify about, okay, so I have 1/3 u to the 3/2 from 9 to 25. And now I'll just put in my values for u. So if I do u being 25, 25 to the 3/2 is 25 to the 1/2, which is 5, raised to the 3rd power. So I'll have 125. Then I have 9 to the 3/2. 9 to the 1/2 is 3. 3 cubed is 27, excuse me. And then all we need to do is just simplify. And if we do that, it looks like we're going to have 98 divided by 3 units squared. So I'm using units squared because it does say find the area. And that's why I have that, whereas if I'm just given an integral, it's not something I need to worry about. All right, last thing. Suppose we have, notice what's happening in here is a chain rule. So you're basically being told, hey, you've got a function inside a function, and then you have the derivative of that inside function. So that's basically saying I've got something that is the chain rule inside of an integral, and that the derivative of this big F is going to be this little f, which is this right here. So since the derivative of this is f prime, this is just the chain rule, of g of x times g prime of x, chain rule, we can say that the antiderivative of this here is simply the antiderivative of d dx of f of g of x dx, because this is equivalent to this, and this is equal to this, and then we have our f here all the way over there. Okay, and that is just f of g of x plus c. And really one of the best examples of that is the first thing that we did today, just reminding you that you take the antiderivative of essentially that outside piece, the inside piece stays the same, but that's done using chain rule. So that is the substitution method.